So in today's video, I'm going to go through the design of a very basic circuit on KiCAD to show you how to use basically the software for PCB design and how you can take it to manufacture. It's going to be a very simple circuit. Don't really have any plans, but yeah, doing my first live stream. Well, first proper live stream. So let me know if you want to add anything to this circuit, and yeah, I'll add components as we go through this. The circuit I had in mind was just doing 3 different LEDs, a connector with 3 resistors in series with the LEDs. So it should be very simple to set up, and obviously we're going to do a through-hole design for this one, and then maybe in a later video. I think I'm having connection issues. Not a good start. Anyway, let's get on header. So something with 4 pins, so we have connections for the 3 LEDs and a ground. So that's going to be our input. And then I'm going to put down 4 resistors. Let me know how the quality of the stream is if you are watching. Can't really tell as the first time I'm streaming on this. Did one too many wires. So now I'm just going to try and find some through-hole LEDs. So what I'm doing right now is basically just giving the symbols that we put down, giving them footprints for the PCB design itself. Obviously, when you're selecting components, you want to try and match the footprints that you're, well, not try, but you want to match the footprints that you have for the components that you've selected, obviously. I'm just doing this as a test for the streaming settings on this. So I don't really care at the moment. Hopefully I'm just gonna see how the stream goes at the end. It's just a bit of a test. Hopefully the audio is okay. If it's not, let me know in the comment section. There we go. That reminds me, I think I should add in some parts for the mounting holes. So let's do that now. I think that's generally a good idea for PCBs, depending on what you need to do, obviously. So for mounting holes, let's go into our footprint assignment tool again and make sure we have them covered. KiCAD is such a good software for being free. It's unbelievable. It's really good. We're just gonna go with M2 or M3. I think they're quite common parts. So now we have all our components. What I'm gonna do is go into the PCB design. It should be a fairly straightforward design, obviously. It's a very simple schematic. Bring in all our components. So we have obviously the 4 mounting holes. To sync the changes over from the schematic to the PCB, press this button here, or you can press F8. When you do it the first time, it's not too much of an issue, but when you do it a second or third time, let's say you realize you made some mistake on the schematic and you need to update it, then you got to be careful so you don't get rid of, or you do get rid of, depending what your changes are, of unwanted components, duplicated components, things like that. So you can see this is a very easy design. It's quite, for me, it's quite enjoyable. Obviously, everybody's different. I do like doing PCB designs, but I guess it's one of the fun parts of the job when you go into engineering. It's quite relaxing, I think. So to rotate components, you want to press the R button. So you can, when you've actually selected it, so to select the component, you would basically press on it. Then you can move it around by just clicking and dragging. And if you press the R, you can rotate it. Pressing the R button, you can rotate it. Basically, what I'm doing right now is just putting all the resistors and everything into place. You can do this how you like. I'm not really concerned with the size of the PCB or anything, so I'm just making a design that looks okay. Changing your snap grid, I think 2.54 for something like this is okay. But when you go into obviously doing your PCB design with SMD components and things like that, I think 2.54 is way too big of a grid size to kind of manage all of this. Right, so let's now place the tracks. What I've done here is make the rat nest, which is basically showing you the connections that you need to make with the copper tracks. So those are shown with this faint light blue line over here. You can turn that on and off using this function here, because when you have a very complicated, I guess, design, it can look very messy, so you can turn it off, or you can make it so that it only shows you some rat nest, or it shows you curved lines as well, which can sometimes make it easier to see. But ideally what you want is the rat nest to be as least convoluted as possible, if that makes sense. Obviously, so that means that we can put our copper tracks down a lot easier. So component placement is one of the most important things you can do right when you first start off the PCB design, because if you get the component placement wrong, putting the component tracks is going to be even more difficult. So now I'm going to connect these up with the track. You can see that the default track that it's given me is 0.25 millimeters. If you wanted to add in different track sizes, what you can do is obviously you can go in and edit this. So let's say I want to change that to 0.5. So that's just with double clicking on this. Alternatively, and what I would recommend is you go into one of these functions here. If I can find it, it's always changing. So tracks basically, and edit predefined sizes. And then in the predefined sizes, you can add in what you want. So let's say I want to go with 0.2 for my smallest tracks, 0.5 for some power tracks, and maybe 1 for some, I don't know, ground plane kind of tracks if I want to. I'm just going to use 0.5 for this. So then you can select your different tracks from here. So what I've done is basically you can select 0.2, 0.5. So I've gone with 0.5. And then if you want to connect up the tracks, or make the connections, you can go to your through hole pad. In this case, press the X button and then click, and basically click the button, your left mouse button again. And you can see it's as simple as that. It's fairly easy to do. It's not complicated at all. But obviously this design is very simple. We can go on to doing a better design later on. or sorry, when I say better, I mean more complicated design later on. What I'm going to do now is just define the edge of the board around the through holes. And finally, let's go and do the copper track, the copper pour, which is called a filled zone in this. So the shortcut is obviously Control Shift and Z. Press this button there. I'm going to go on the blue plane and name it ground 1. That's basically my PCB design done. What you can do is change these little tracks and make them wider if you need to. You can bring these components in. One of the other good things about KiCAD is that you can look at this PCB on 3D viewer as well. Sometimes it makes it a bit easier to see what you're doing. You know, I think the best thing about it is looking at your silk screens and see how well you've aligned them, because sometimes you don't want them going over your copper pads or your cutouts or different regions in the board itself. So obviously I put down the filled zone with this on the ground plane. I did want that a bit further away, so I'm just going to correct that. Then if you press the B button, it will fill in the zones, and you can see that the blue track is now filled in. So that's all the ground connections. And then if you want to see this, how it looks in 3D, you can basically just press the 3D. So you can go here, so view 3D viewer, and then look at this in terms of how it looks when it's finished. So you can see obviously we've got our mounting holes here, we've got the copper tracks going to the resistor and then towards the LED. And then the bottom of the board, obviously we've got the ground going back towards this. Obviously two layer boards can be a bit more expensive than normal boards sometimes. I'm not sure anymore, maybe because PCB boards have just gone so much cheaper lately. So yeah, but what I'm going to do is we can just, because it's such a simple design, we can use a single layer board. So I'm just going to remove the ground plane and replace that with a track. So let's see what that looks like on our 3D viewer. So obviously there won't be, I mean, these, I'm not going to build this up anyway. It's just for a bit of fun and learning on KiCAD. So you can see got the LEDs connected, and I've got a single track for the ground going back to this pin here. So to turn on the LED, what you would do is just put this to like 3v3 volts, 5 volts, and the LED would light up. It's a very simple board. Another thing you can do to make the boards look a lot more professional is use this arc feature on KiCAD. And that basically what you can do with that is, I don't want a full arc, so let's see if I can. Not do the full arc, please. I don't use this very often, as you can probably tell. I think I'll need to change my grid size over here so that I get the part that I need covered. I mean, I can just do it using, normally how I would do it is just using the numbers over here, which, it basically perfectly aligns the tracks that I'm putting down. So the line width on this is 0.1. I can see the line width on the arc came up to something slightly different. I'm just going to change that. You can see I've got a nice curve on this now. This is, yeah, I think that looks better, a lot more professional in my eyes anyway. If you look at that on, oh, it's not connected properly. Brilliant. You see the end point and the start point. So on the x-axis and y-axis. So what I want to do obviously is connect this point up to here. It should tell us where it's not connected if we run the DRC rules, hopefully. Where are the errors? Violations. So this point is not connected. I'll change that to 0.1 again. Let's do the DRC again to make sure they're all connected. Nope. That 1, 2, 4 and 78, 74. 1, 4, 2, 78, 74, 78, 74. I'm not sure why it's moaning. I think that's connected. 14732, 14732, 5334. Let me do this to the smaller size as well. So I mean that's basically it. I know the board outline is being a bit weird, but I'm not too sure why. Run DRC again. Delete all. Excellent. Let me try that again. See if I can fix it. Delete that. So what I'm going to do first is make the 90-degree track. Okay, so I've got the edge outline over there. Change that to 0.5, 0.1, sorry, and then connect up the track from there. So let's try doing that. So I'm going to change the, I mostly use Altium, so let's see, still learning here and trying to show as much as I can. So delete all of this, delete the markers, and then add in this line over here. So we've got 90 degrees. Excellent. Let's put in the lines now. So this should technically be connected. But what I've done obviously is make it too bloody big. Let me put down a fab line just to guide it. What I'm going to do is go back to edge cuts and start from there to there. Delete the fabrication line I put in and then connect these 2 points up there. Done the same thing there, so let's put a random line in as a reference. Put the arc back on the edge cuts layer, which is what the PCB design house will use as a definition for the edge of the board. Go back to the straight lines, connect that up, connect this up to over there and this up to over here. Then we have basically a nice neat little board. We can add in our logos and stuff if you want. I mean, I'm not really that bothered. It's just this. I mean, this I'm just doing to test the stream. So yeah, hopefully this was going well. And if you have any obviously suggestions, just let me know in the chat. If you have any questions, let me know in the chat. And I'll be happy to help you as much as I can, obviously. There you go. We have the PCB design all done. Now to basically how we can create the manufacturing files for when we want to design, take this board from design to physically made. One of the PCB houses that I use quite often is JLC PCB, which are very cheap, and they do provide quite good quality boards. There are some alternatives, like I've used Osh Park before, which they did have a decent quality, and they generally, I think, make purple boards. So if I show you that, so there's Osh Park. I think this is an American-based company. And there's JLC PCB. These are really good. You can get the boards back to use very quickly, and they're very cheap as well. So what I'm going to do is use this. But in order to get the boards made, you need something called Gerber files. Gerber files basically define all the parameters of the board itself. So and they're separated by layers. So each file, when you generate the Gerbers, or when you generate the manufacturing files for a board like this, they will have multiple layers, and each layer will have its own file, and it'll be typically labeled as, let's say, GTL or GBL or something like that. And those extensions mean basically that, oh, let's say this is the top layer copper, or this is the top layer silkscreen. So to create the Gerber files, you basically need to go into this plot button over here and select all the layers that you want to plot. So obviously if you had a 4-layer board, you'd have 4 copper layers. In our case, we've only got 1 layer, but I'm going to print both the copper layers. The paste, obviously, which we won't need as this is a through-hole design. We want the silk screen because that will basically put all the labels for the resistors and the LEDs. And we don't really care about much else at the moment, but what I'm going to do is just print it all out. Create a folder inside my project folder called Gerbers. Select that, press yes, and then plot. So this has generated all my Gerber files. Then generate drill file. So this is basically the file that tells the manufacturing house where to make holes in the PCB and what size holes they should be. So it defines the size of those as well as the location. So if I go show you where the files have been created. So as I said before, you get a file per layer. So you got GBR. Okay, these are kind of labeled slightly differently. I think all softwares do it a little bit differently. On this is not as an extension. It's just labeled in the file itself. I believe JLC PCB want a zip file when you upload to here. Maybe they are okay with custom files as well. Let's see. If they don't accept this, then we'll put in a zip file. I think they need a zip file. So let's do that. Send this to a compressed zip file. Let's call this basics.b, whatever, that's fine. Test PCB. So the design that we have on KiCAD, obviously, is very simple, but it's this this board here to kind of view it in the 3D layer. We have our silk screens, our 3 resistors, 3 LEDs, the connection header, and the mounting holes for the PCB as well. I mean, I'm not going to build this, but if I was going to build this, I'll probably look at the clearance on this hole, just make sure that it's okay and it's not intruding with the LED here. Obviously, this board can be a lot smaller if you need it to be, but I don't really care. It's just for learning, obviously. Now, the reason I'm looking back at this is because I want to compare it to what KiCAD has picked up, which is I've got the silk screens, I've got my components, I've got the copper tracks on the top layer, I've got my mounting holes. So it's all looking good. It's all basically as we would expect it. So if you wanted to go and manufacture this, yeah, it's 2 days build time, £2. It's brilliant. Yeah, and then you can get it different colors and things as well from JLC PCB. Let's try this with Osh Park to see how much it would cost there. There are some other ones. I mean, I've used these two before. I've not used anyone else before, so I wouldn't recommend anything I've not used. Obviously, I've had good experiences from both of these companies. Though Osh Park, the delivery time was a little bit longer. This was about 6 years ago, mind you, so they might have improved a lot since then. You can see on this the 3 boards. Obviously, they're gonna cost us 12 quid, whereas the boards on here, I'm not sure if we've defined a quantity yet. Calculated price, PCB quantity 5. I think this is per board, so you can see the cost difference is huge. There will be a shipping charge, I think. Let's see what the shipping. Okay, I don't want to make an account, so I'm not going to do that right now anyway. I can make an account later. But you can see, fairly easy board, fairly easy design. We can make this board a little bit more complicated if we want to. I don't know, let's add in some SMD parts or something. Let's add in a regulator maybe. So basically what I'm going to do is move this along on the bottom, move this down here. It's generally a good idea to add in a label. So if someone else was designing this PCB for you, then you would want to relay all the information that they should be aware of on the schematic. So let's say you want a clearance of I don't know, just random 2 mil from this component, you should state that somewhere. You should give a rule to the PCB designer so that they follow what you need. I mean, most of the time, I mean, I don't know. It's likely that you're designing the boards, and then you still might want to do that because it helps you avoid mistakes, which is the main thing. Okay, I'm gonna go and try. I'm gonna try and find a regulator that we can use for this. I'm just gonna pop over to analog devices. Products, and I want power management generally. Yep, there we go. Let's see if we can find a nice switching regulator, buck converter. Step down. And is there an option to explore step down buck converters? Okay. View all ports in this category. Whilst that's loading and I put the numbers in, so I think let's say the input to this is you're going to use a USB socket or something like that. So I think the range for that is 4.75 to 5.25, and let's call our output 3.3 for a microcontroller and a current output of, let's say, 0.15. Let's call it 0.2 amps. That would generally cover the needs for most microcontrollers unless you're using something very fancy. And it should cover the LEDs as well. I don't think at this point I will add in a microcontroller. It might take too long. I'm not too sure when I'll need to finish this stream. So yeah, obviously, let me know if the quality is still good. It's my first time streaming on this, so. And let me know if you find this useful, because obviously not all of you will find this useful. I think it's kind of intended towards more beginners. Not that I'm that advanced myself, you know, I'm learning as I go as well. So we've got a list of op amps here, which all will be suitable. I just want to find something very simple and hopefully something that's already available on KiCAD. I mean, if it's not available, that's fine. I can show you how to design the footprint for it as well. These are some very complicated parts. Let's have a look at this. 140 volts. Wow. I don't think I want to go that high. Let's there must be simpler parts than this unless I've done something wrong in here. I've got 0.2 amps. I don't think I've done anything wrong here. I don't know. There should be simpler parts somewhere. Oh, we've got a nice QFN part. That might be. I don't want anything that complicated. There we go. That looks alright. It's a fairly small part. LTC3549. I'm going to go with this. And I'm just going to use the basic design that they give us, because otherwise we're going to be here for a few hours trying to get all the components together, which I don't want to do, obviously. So let's first of all just put the schematic together, and then we'll look for some of the components. That most of the time, places like Linear Tech, Analog Devices, oh well, they're the same company nowadays, but places like them, they will give a recommended PCB layout, which is very handy, especially for us beginners. And then we should try and follow that as much as possible to avoid any problems. You know, so it's obviously tried and tested. There's always application notes as well, which can be very helpful when we're doing this. So I'm just going to try and find a reference design. Generally, they will have a reference design in here that does exactly what we need. especially for something simple as this. So there's an application design. They've got V out of 1.5, so now I want something that's a bit higher. Let's see what nope, they're all just doing 1.5. Let's have a look at another one. Obviously, I want to try and keep this as simple as possible, so I don't want to go through the whole design stage of a buck converter, which we might be here for an hour or two. So we have a 12-volt output design, 5 volts, and a 3-volt output design. Excellent. So this is exactly what we need. I'm not going to go ahead and calculate this. I mean, because obviously this has 4 volts, 240 volt input. I think we can optimize some of these components when we're just doing, 4.75 to 5.25. So what I would recommend is you go through this data sheet in detail, calculate all of the components properly, and do it so that you're optimizing for your design and your needs. I'm not going to bother because I'm just doing a kind of a tutorial on tutorial on PCB design using KiCAD. So you see we have a capacitor, we have another capacitor, we have one more, another one, we have a resistor, which I'm going to I want SMD parts in this, so I'm going to try and use SMD parts. So we have a resistor across this, and we need an inductor over here. Now what I'm hoping is that the component is already available. If it's not available, I will just basically need to design one, but that's okay. That's not too much of an issue. I'll show you how to do that. So LTC 3658. We don't have 58. Let's see if this one is a close match. So we have 38. We have SS pin, we have ISET pin, obviously you have the feedback pin, we have the FBO. I'm not too sure what that does, but it's been left unconnected anyway. Just make sure that this matches what I have. So it's a 3.3 by 5 part. Obviously you have MSOP, 16 lead MSOP. I think this part will be okay. I'm just gonna make sure that the pinout is okay, and then if it is, I'm just gonna use this part. I think if you're doing this for a proper job, you would want to design the part using this as a template, to save time and doing things properly. Where's the pinout? I missed it. So pin 1 we have SW. So pin 1 SW, pin 2 we don't have. Pin 3 is V in. Yep, that matches. Pin 5 is FBO. Pin 6 is V program. Pin 7 is V program 1. Pin 8 is ground. Pin 9 is VFB. Yep, and 10 is SS. 11 is ISET. 12 is OVLO, so over voltage lockout, I'm guessing. We don't have a 15. 14 is RON. 16 is ground. Where is 16 on here? We don't. Am I just blind? We don't have pin 16 on this. Pin 8. We do have it on the component, so I will just have a look. So we do have it here. I'll make sure that it's connected in the design itself. So let's put this part down and go down to our reference design. For the 3v3. So I'm just going to be following this design. And then what I'll do is add another connector for the 5 volts. I'll add in a USB connector. USB-C, power only. Let's go for that. I do like the USB-C connector. It's a lot better than your standard other USB-C connectors, but they do need 2 resistors. And I found this out after doing one of my videos earlier, and someone commented it. So that was quite helpful. So thank you, viewer, who commented that. These 2 components, they need to be 5K1 resistors. And I'm going to connect that up to the ground over here and make sure that it's on the same ground as this. So I get, if you see these random things pop up, it's because I get confused between Altium, which is my main software that I use for the PCB designs I do for my job. So yeah, just bear with me if I start using random shortcuts, because I use LT Spice a lot, so I have shortcuts in my head from LT Spice, and I have shortcuts in my head from Altium and this software, so it can be a bit weird sometimes. What I want to do is connect up the V in to the V bus pin. Well, let's connect this up to the V bus pin first. And to connect that, obviously KiCAD is just improving massively. Every few months there'll be a really good update. So when you hover over the pins, you can basically just create the component that you need. Run, they've got it connected to VN, so that's what I'll do. iSet is connected to these 2 components here. I will make sure to put down these parts. So this obviously is a 1 microfarad capacitor. What I will do, because I like having some bulk capacitors in the input, is put another capacitor in here. Keep that close to the connector, and keep this one close to the pin of the regulator. So I noticed some of you have tuned in. How are you guys finding the Art of Electronics videos? Are they helpful? I mean, are you guys going through that book? I mean, when I first started electronics as a career, I used that book so many times just to learn some of the concepts. And yeah, it was very helpful. So and one of the things what was frustrating for me at the time was just trying to find solutions. I would answer a question and then try to check somewhere, oh, have I done it properly? And I could never, it was so difficult to find a solution. I was like, you know what, that's something I can do and something I enjoy doing. So hopefully, you enjoy the videos as well. I've been trying to improve my audio quality and everything, because I'm not really a content creator, to be honest. So I've done that wrong there. So it goes to prop 2. So I'm not really a content creator, but I do I am trying to make the audio and the video as well, obviously, as engaging as possible, because I don't want people to get bored watching that. But it can, it is difficult to make that content more exciting, to be honest with you. But yeah, hopefully you guys are enjoying it. Yeah, obviously I might not get everything correct in there, so if you have any comments and feedback for me, that'd be fantastic. I'd love to take that on board and improve my videos in the future, and just like, yeah, improve my electronic skills as I go through all of that. So what I'm doing now, is just, yeah, just finishing off connecting all of this. I mean, so whoever's done this layout is a bit weird, but ideally I would have liked. What I'm gonna do is rotate this. I don't like doing this, but it's gonna be neater than trying to take this track. Okay. I don't like doing it, so I'm not gonna do it. I try and stick to that for my job as well. Just you don't want to do a half-assed job, I think, generally speaking. But yeah, so FBO is unconnected. V feedback is after the inductor, so that's what I'm gonna do. And then this goes out to the 3v3. I'm gonna put down a power plane. So I like the ones. This is where I like Altium a little bit better. I like the PowerPoints with the bar on top. I don't quite like these arrows. It's just maybe weird, but whatever. That'll be fine. So we have our 4, 7, and we have a connection to the VFB pin, and we have a DRC, so a no connection flag on this pin. So you do this, basically, if you had a very, let's say it's 5-6 page design. Oh, hello, another one. I'm glad to get my first comment. If you had a very complicated design and you do a DRC check, a good software should flag up anything that's not connected. So obviously that's just making sure that you haven't basically made any mistakes in terms of your schematic capture. But if you have a microcontroller with 144 pins, it's very unlikely that you're going to be using all the pins when when you're doing your product. So what you would do is you would add in a no DRC check flag onto the pins that you're not using. And what that does is basically it makes sure that when you do a DRC check, it's not flagged. So if you don't flag it, what happens is basically the software will just return errors that you unintentionally missed, I guess. So it's a good tool, and I think you should try to basically follow that tool, or follow that no DRC thing, for more complicated designs. Obviously, for something like this, I don't think it really matters. So vprog1, and I've missed one connection. I want that to be connected to this node here, to the ground. And I think that's everything we need. Obviously, I'm going to label up these components. 100 microfarad capacitor seems a bit too large. I don't know. Some of the designs I've done before, I've not used a 100 microfarad capacitor on 3v3 regulators. Maybe this is for something specific. It's not particularly high current as well, so yeah, it should be fine. I mean, we've just selected this very quickly, haven't we? So that's all right. Thank you for that comment, Delta Engineer. Yeah, I'm still learning as I go through. I think the last one I uploaded took me a few hours to work out because it was quite complicated. But yeah, it was good fun. I really enjoyed that last one I uploaded. I think it went live this morning. The questions are getting a little bit trickier. I mean the next question, which I'm kind of just putting the video together right now, it's not as tricky, it's simple. I think that's going to be a 2-3 minute video, so yeah, that'll be good. So what value is this? This is a 470 nanofarad capacitor. So basically that's the SS one and the VPROG2 one, and the iSet capacitor is 220 picofarads, and we've got a resistor of 220 kilo ohms. I've not looked at the datasheet in details. I'm not sure what they do, but yeah, if you want to review the datasheet in more detail, do that. Well, I would definitely recommend doing that if you're going to use this for something serious. You know, if you're especially if you're doing a project and you want it to work. Don't just follow the design that's been given to you, because they might have optimized it for something that you don't want to. So yeah, just something to be careful with. So I've got all the components in place. What I'm going to do now is run the footprint assignment tool, which is on this button here. 1 microfarad and 10 microfarads. I know I can get capacitors in 1206. The 100 microfarad capacitor, I've not used an SMD one before, so I think I need to search for this one. This is, my first go-to is always Farnell, because I prefer the search function. Let me see what size I can find these capacitors in. So ceramic. I think they're going to be quite big. I want a minimum voltage of, I think, at least a 6.3. Just because what happens is when you use a capacitor close, let's say if I was using a 4-volt capacitor and you're running it at 3.3, and if you look at the datasheet for capacitors, they'll tell you how the capacitance of that component degrades with the voltage. So as you get closer to the operating or the maximum operating voltage of the capacitor, the capacitance itself is a lower value. So you want to keep that in mind. And obviously, if you can stay away from the maximum operating voltage, it will also give a longer life, I believe. So it's that's a good idea. Also, we can find these in 1206. So I'm gonna use that. Let me show you what I was just talking about, if it actually exists on this datasheet. Sometimes they don't give it, but yeah. I mean, this datasheet's a bit nothing. Sometimes, yeah, they'll have pretty graphs, which you might want to look at. So 1206 on this as well. If I can find the bloody thing. These two I should be able to get 0603s, no problem. And the diode. I think for the diode, let's see what I can find. I think generally speaking, you can just get a SMA one. It should be alright. I'm not going to go into too much detail here. 68 microfarad. Farad? Did I put farad? Well, that's a bit silly. So obviously for this, I want a microhenry inductor. I'm just going to go for a large inductor with like 5 amps peak current or saturation current, and I think that'll be okay. So go back to the footprint assignment tool. Go to the inductor, and let's see if I can find any inductors here. So inductors, SMD. Just gonna go with one. I think it should be okay. And these two, the resistors. It's so good having these packages. I think before it was difficult to get these packages, maybe 10 years ago, for this software. SMD and 0603 hand solder. Apply. Oh, I missed one. 0603. So we basically got all our components. So let's transfer this over to the which domain? I'm gonna type it out because I think there's a slight delay on my stream. A single board computer. I mean, I've designed a lot of microcontroller boards. I've not really done a single board computer as such. What I would recommend is trying to get a design file for like a Raspberry. I don't know how complicated you want to go, obviously. So take this with a pinch of salt. But what I would say is start off with a Raspberry Pi, something like that. Or I think they released a smaller version of the Raspberry Pi as well. And there'll be a reference design for that on the internet somewhere. And I would use that as a starting point, and obviously introduce in there the things that are important for your specific needs. So obviously map out, what you want to do in terms of memory, what hardware features you want, and then go from there. I think that would be kind of the starting point I would suggest. I can look at it for my channel. I think it's a good idea, and I think it'll be a good learning experience for me as well, really. But if you have any specific questions, let's say you're adding a DDR3 RAM or something like that, I can certainly help you with how to lay that out. I've used high frequency memory chips and things like that before. It really does depend on what you want to include in terms of your hardware and what your requirements are. But yeah, no, it sounds like a really good project to kind of get hands-on experience with, not with just analog electronics, but yeah, mixed signal design. Yes, it sounds like a really good project. What I'm going to do now is go to the PCB design and delete my edge layer, move the mounting holes out the way, and then add in the SMD parts. So this is just going PCB design into a bit more detail, pressing the F8 button, which is basically updating the PCB with changes made to the schematic. So replace any footprints, that's fine, because this is the second time I'm updating it. I want to make sure I'll make sure I read this properly. I think that those ticks are fine. We should have all the different components that we need. Well, I'm not happy with that diode, it's huge. I'm going to go and change that diode. I thought I selected something, maybe something that I could work with, but maybe not. Footprint assignment tool, go to the diode, and let's find a slightly smaller one. I mean, if I was doing this for my job, I think I would, I'd do it properly and find a diode first, and then come on to do this. And that's what I would recommend you do as well for your projects. Oh, by the way, how's the audio? I've been messing around with my settings, and throughout my videos, I've been trying to get it just right. I think I think it was slightly on the low side, so I've added some gain. I've added some noise filtering, and I've added the noise gate now. So I think it's slowly improving, but let me know how it feels. I got myself a nice condenser mic as well. You know, so that it's not so it's easy as possible to follow these. You know, you don't want to be following videos with poor audio quality. You know, it's never interesting and it can be a pain. So just replace footprints, relink, delete footprints with no symbols. I mean, I did that manually anyway, so that's fine. So I've got all my components here. What I don't have, and I think I've probably forgotten, I think the inductor is probably too small as well. Just looking at it, I think I forgot to assign a footprint to this. Yes, I did. It's just because it's been offset by such a large amount. So connector, USB, top mount, horizontal, 6-pin, receptacle, GCT. I think any of these should be okay. And then the inductor, I want to go slightly bigger on that because I know, just from experience really, that probably won't be enough to find a 68 microhenry inductor with the current ratings that I want, but not that I particularly care anyway. Just going back to what you said, another one. If you have any questions or anything, you can just post a comment on one of my videos, and you know I do check through all of my comments. Oh, thanks for the feedback on the audio. I do check through all my comments. So yeah, I'll get back to you. And obviously, if you wanna go through something now as well, you know, I can just switch over to that as well. Right. So save this. Update the PCB again. Delete footprints with no symbols. Yep. Relink schematic symbols based on the, I think so. There we go. So we've replaced the inductor with something that looks like it will work. So now let me just move this out the way, and then I'll just kind of focus on the SMD design. So I've got the USB-C connector over here. And then we obviously have, let's just look at what that looks like. So just want to make sure that it's okay. Yeah, that should be alright. By the way, you can get, you know, if you want to kind of fully 3D model stuff, so USB-C 3D model. Obviously, if you found a specific USB-C connector, you just want to approach the manufacturer. Sometimes they'll just have a 3D model or step file on their. Sorry, bear with me. So sometimes they'll just have a 3D model on their website, and you can just download it. Other times you might need to find something. What I'm going to do is move the schematic to the other screen, so I know which part. Oh, let's do it side by side. Otherwise, I think it's better for you guys when you're viewing it. So one of the good things about KiCAD is if you click this, it will show you that component. You know, it will zoom into that component. So what my idea was with this was to connect the capacitor close to the inductor, unless, you know, imagine it's a big board. You want to keep the 1 microfarad capacitor as close as possible to the chip. The reason you keep it close to the chip is to minimize track inductances, and obviously inductors or parasitic inductors in the tracks themselves can cause your voltages to dip. So if you have a short track, is generally a good idea. So to minimize those inductances, I'm gonna change the, so as I was saying, if you have a SMD design, it's generally a good idea to change the grid size to be something smaller. Otherwise, yeah, it's not. Should have ground on both sides. Yep. And then let's go and do one thing, which I did recommend in one of my earlier videos, is adding net labels, which makes everything so much easier. So what I'm gonna call this is 5 volts. Actually, for this, it's better to use the power symbol. So let's see if they have a 5-volt symbol in here somewhere. 5-volt power. Yeah, that should be all right. And then I'm going to label some of these nodes so that it's easy for me to track this along. Actually, the other nodes are okay. That should be okay. I don't have anything too complicated on this, so that's fine. So bring in the changes from that side. And then what should happen is this should change to the 5 volts positive, which it has done. So to rotate the component, obviously click on it, select, drag it. You can drag it around, press the R button, and it rotates. Simple as that. So I'm going to put that down there, make just, most of the battle with something like this is getting the component placement right. And obviously I did suggest that you should be following the recommendations of the manufacturer. So let me follow my own advice now and go to what they did. In terms of the software, they hopefully, I think if it's your first project, because those kind of things can get really complicated, what I would suggest you follow something that already has some software available. And I think that would be the best thing to do. Because if you try and write an operating system and things like that, it will get way too complicated for a first project. So if there's something already available, that's what I would recommend. Obviously, and I'm not 100% sure if there's a specific definition for a single board computer, but things like what I've used in the past, let's say, microcontrollers, right? Um, some manufacturers have a lot of tools available. So you can basically use their drivers for things like SPI and I2C and things like that. They will provide drivers. So if you're selecting something that's quite popular, you should be able to find the drivers hopefully quite easily. But yeah, I mean, for a first design, I would stick with something that people are already running with. Hopefully, there should be some guides on the on YouTube. So yeah, hopefully that helps. And I know it's not that much help. And I don't want to advise you wrong as well, so there's that as well. So all I'm doing here is copying this layout. We've got the closed capacitor, basically C in over here. Got C out on this side. We've got our inductor on top. What I've missed is the diode. So let's go ahead and add the diode in this chain here. So all I want to do is basically copy what's being shown to me, and for as a beginner, that's probably the best thing you want to do. And then when you're trying to optimize designs, and as you understand the designs a lot more, you know, you can start tinkering with what we're doing right now. So another one, if there's anything particular I can help with, I mean, I've done like HDMI hardware and stuff like that in the past. So yeah, I can drop some schematics for you on my future videos on, you know, how you would go about connecting HDMI or USB-C for power delivery and things like that. So obviously, creating a video takes a little while, and I'm not sure how fast you want to move. So I've got the 5V connection on this side. I've got the ground connection on here. Then my V out connection is on this side. And I believe that RAM and flash. Does a Arduino, not Arduino, sorry, does a Raspberry Pi have external things like that? It might be, I'm not 100% sure. I mean, I've looked at the bigger one before, but that was maybe 5-6 years ago. Raspberry 2 or 3, I can't remember anymore, to be honest. But yeah, start with the reference design. See what they use, see how they're using it in terms of the in terms of, you know, the design itself. So this is going to 5VP. So those are two capacitors. I want to find the resistor that's going to 5VP. Oh, it's not going to 5VP. Pin 14. Have I made a mistake on my schematic? Something doesn't match up. I don't actually have pin 14 goes to run. Okay. So obviously this design is slightly different. What I'm copying obviously is this layout over here, and the run is connected directly to in. So I'm going to ignore these two components here, and then for ground 1 pin 12, they've got that R4 going to ground. Okay, so this is going to be easy to follow if I basically label the pins. So what I want to do is pin 9 is VFB, so that's going up back to 3v3 as well. This is going over here, so I'll line that up. Oh yes, for DDR, there's many different things that are quite important. Some of the things like your track characteristic impedance, your load impedance. Obviously, you want to have clearances to nearby parts. You want to make sure that the track lengths are the same, so then you don't get much propagation delay. There are some calculators online that can help you calculate your characteristic impedance for the tracks and everything like that. I know, I think for USB you try to aim for 90 ohms, but I'm not sure what you would aim for in terms of DDR3. I'm sure it's important though, so this one, R5 and R6 go down here. So yeah, there is a lot to learn, but I think, you know, the project that you want to do, I think you will learn a lot. And when you, I don't know if you work somewhere at the moment, but when you go for interviews and present something like that, you know, it is very impressive. So if a candidate came to me for an interview and they presented to me a single board computer that they've designed, you know, they'd probably get hired. It is very important. C2 goes in parallel with this one over here. And then we have the last component, which is C4. So C4, I'm going to put down on pin 6. Be right back. Sorry about that. I'm back now. So what I'm doing now, just connecting up this pin over here. So that goes to pin 6 and 10. So 6, I think, is on this side. So this is going to be the tricky one, I think. Yeah, this connection is going to be the tricky one. But it should be alright. Should be fine. We got ground on this side. Let's just have a quick look at the reference design. So we have these two pins connected to ground. So yeah, they've separated the ground layers, which is fine. We've got so the ground is going internally there as well. So I'm going to move this. Let's look at the reference design again. So the 470 goes SS and vprog2. vprog2 and SS. So yep, that's fine. So I do need to connect it up that way. Just making sure, because the reference design is slightly different to what we're doing here. So have you made any progress on the single board computer, or are you still just looking at the kind of the design, or you know, just speccing it out still? What I'm going to do now is put down a ground pour, which obviously you can do with this, and then I have ground 1. What's going wrong there? Why is that? Add a filter zone. I want not edge cuts. I want copper, fill ground 4. I want ground 1. So basically I'm just going to cover all the ground pins. And make sure I get a nice solid track, basically. Sometimes I hate it when there's overlapping bits and you can't select the component you want. So I don't want this as a thermal relief pad. So if you double click on this and press the E button, you can edit your ground pour. So you can see right now that it's making these lines. Basically that's called thermal relief. And what that does is, if you're it basically prevents heat from spreading too fast to a copper layer. So let's look at, for example, the part we had here. So if I had a full copper layer on this node here, it would be relatively more difficult to solder this part up, because you would need to hold your soldering iron on it for a lot longer, because all the heat would be just dissipating in the copper. So obviously I'll remove the thermal relief, so you can see now it's just a solid plane. Keep on my reference design. And then the next thing that I want to do is the 3v3. Where's V in? Which pin is V in? V in is pin 3. So it's this side over here. I just need to make sure I connect up pin 14 as well. So how is the reference done? Because I was just looking at the reference. I wasn't too happy with what they've done over here. Okay, yeah, obviously I'm looking at the wrong node. That's what it is. Yeah, VN is fine. It's the 3v3 node. It's not going down there. It's alright. I thought 3v3 was the VN node. Obviously, it's not. I accidentally did that on the wrong layer. So if you want to correct that, obviously double click that and you can select your layers here. And I'm going to put it on the right side. So we've got our 3v3 plane over here. Just tidy that up. This doesn't matter as long as you have a nice thick track. I mean, my circuit is quite low power anyway. So yeah, it should be alright. The next thing I'm going to do is, what's this connecting to? So this is I might need to bring this one out a little bit, or maybe go with a bigger capacitor. If I bring that out and then take my copper pad underneath, what node do I want? I want node D1K. So this is why it's a good idea to kind of label these nodes. So D1K. So it's this one here. What I'm going to call that is the switching node. I think this is one of the most important nodes in when you're doing converter designs or boost converter designs, because this has a very high frequency pulses on it. So you want to make sure you get that right. Just update my design from the other side. And you can see that it's relabeled to VSW, and hopefully that should be as well. So that makes it a lot easier to follow, as you can see. I'll make sure the clearance is okay afterwards. Oh, that's a neat idea as well. I think antenna designs and things like that are very difficult. I mean, I've never fully looked at, doing antenna designs myself. What I have done is used development boards which with the designs already in place. And yeah, they're quite cool. What I want to do for my channel, and I think it'll be quite interesting, is basically make like an RC car or something like that. Something fun, I think that'll be interesting. So you can see we've got the copper pads here for the C1, and this layer automatically creates a gap clearance, or the required clearance, and that clearance is created from the rules that's been set up or predefined in KiCAD. What you want to do is make sure that the PCB manufacturer can meet that clearance. Otherwise, you might have problems. So bring that up there, bring that up there. Bring this down there. So that's CC1. Let's see how this is going to work. I think this USB connector for USB-C is just getting so much complicated for PCB designs. There are a lot of references available on the internet, obviously. Strange, why can't I line these up? Yeah, that would be quite cool. I think those sort of things kind of bring in the viewers as well. Not that I particularly care about just kind of growing my channel for the sake of it. But yeah, it is something that I want to do. I think it is interesting, and you do learn a lot in terms of electronics. So let's put in a ground plane, sorry, not ground plane, but just a copper plane for the 5-volt input. I'm just so habitually calling it plane that it's just second nature now, I think. So I think the pin is around here somewhere, so that should cover it. If it's any conflicts, I will change it. What I want to do is make sure that I get the pin nicely in there. I don't need all of that, but that is not looking great. To be honest, I might take this on the other side of the board, the CC resistors, so that I have a nice 5-volt input. So to do that, basically crop a track, red track there, then you bring it out, press the V button, and so that creates a wire. Connect that up there. Delete this track over here. And then this one, oh, I used the wrong color track here, wrong side. I want that to be on the blue side, and then I'll need to translate back. I'm sure there's a more efficient solution, but yeah, this is what I'm keeping with for now, and then we can update it later if we need to. Go to the other side, blue track, go back to the original side and connect that up. And then obviously we have our ground. I mean, this is not too much better. What I'm going to do is change the size of this wire. Let's go for 0.2, 0.5. Wait, I think that's from memory anyway. I think manufacturers don't typically have a problem with that size. I might be able to take it on the back side actually. Thinking about it, that might be a lot better. Let's do that, and then we don't have to worry about it. So there's always improvements. And that will allow me to end this a little bit earlier so it doesn't look as messy on the back. So we've got our 5V connected, we've got our the switching node connected, we've got the 3v3 node connected. It's looking good so far. What I'm going to do for this node, I think because this is just the enable input, I don't believe it's anything, high frequency or anything like that. So I will just take this on the other side. for now, and I'll see if I can improve that afterwards. This is, oh, so they're both, so this is connecting to this node here, and that is connecting to that node. So take that out there. And we have this. So I want that obviously to connect to the ground plane, and that connection there. Now, if I was doing this properly, I would, read up a lot more detail about what this is doing. I'm guessing that's soft start. Yeah, I'm guessing that's soft start. So might be okay with a connection directly from there, but I am going to put down the ground plane first, and then route around for the other one. I'm doing the ground plane first because I want to make sure that my ground plane is good. That's fine. Why did I? Oh, it's because of the clearance from this one, because it's a small component, so that's okay. Now the last thing I'm going to do is connect up all of these components. I can afford to bring these a little bit closer, I think. And the final thing I'm gonna do today, and then I think I'm gonna call it a day for now, is connect up the underside of this. And then use loads of wires, as you can see on this design here. I want, so predefined sizes. I'm gonna add in 0.5, 0.2. I think even that might be a bit too big, but we can change that later. So 1. See, I've got that track going, which is probably not a good idea. So let's connect up the wires, and then we have connections between these two points here to the other side. So yeah, it's going to be a little bit of moving things around for now, but I've got the main bits already in there, so that should be, in terms of how the buck converter works, that should be alright, because we've got the important nodes already connected as they should be. We can take that out all the way around, and that won't be a problem. So connect up all the wires. Just make sure we have loads of good connections to the other side, and we're not clipping anything with the through holes as well. We've got the L1, I'm going to put that down there. The ground is all connected. I mean, that's a simple connection there. I don't particularly, yeah, I'll just connect up there, it's fine for now. Connect that back. And these nodes, and obviously they need to go to the ground plane. They can just go through there, that should be okay. I would maybe make those tracks a little bit bigger. And then the last bits, you can see I've got some nodes here that need connections. So this one here is going to be a little bit difficult. Go to my predefined size. I think I just did all of them wrong, so excellent. Let me change all of them. So yeah, with the smaller wires, obviously you can see now I can get a few more in there. So that's what I'm going to do. So nice solid connection to the ground plane on the other side. And basically do the same thing for this. Move this out here, move this out here, and I don't think that needs anything that's, that's not going to be anything too demanding. Obviously I would make sure that there's no high frequency components going from that track. If there was, I would make sure that we have multiple wires to reduce inductances and things like that. Right, and then the last thing is connecting up this node, and it looks like we'll have to basically go around this one. What we can do is take a copper track from here, bring it round as far as we can take it, and then switch over to the other side of the board and go like that. So we've got our design. Then I think just a few more connections to go, because obviously it tells you what connections I've missed. It's a fun investment. I don't think it's a good investment. Particularly how cheap PCBs are nowadays, really. Just because PCB prices have dropped so much. I don't think and the fast turnaround as well. I think the advantage a engraver might give you is that you can probably turn around something in a day, which would be next to impossible. But obviously it's quite expensive. Yeah, and obviously you might depending on the quality, you might struggle with some finer pitches, but you might not particularly care. So pin 12. Pin 12 is that one there, and in our reference that is connected to ground. Okay, so basically going to connect this to this ground node here, and that should be fine. The last thing that we need to do is this one. I can't believe I missed it. Oh, so I shared some with you at the beginning of this stream. I'll just go through them again. So there's a JLC PCB, which is really good. You know the board I just designed a little while ago, using the LEDs. So these LEDs there, that board basically would have costed. So I was just going to upload that board's file. So it's uploading the PCB files in there, and you can see the with promotion, and I mean it's a fairly small board. You can see the dimensions here is 5 centimeters by 3 centimeters. It's $2 for 5 boards. It's very cheap. Another company I've used before is Oshpark. And Oshpark, basically, I think it's a bit more expensive. I think they're an American-based company, whereas JLC PCB is a China-based company. They might be able to deliver to you faster in the US, but from what I remember when I used them about 6 years ago, the delivery was about 15 days. But again, they're not too expensive. You can see that, it's $12 for this board. So yeah, it's not bad at all. So just bring this over, and so I'm gonna rush it a little bit now because I do need to head out. So sorry about that. And then the last connection I need to make, which is going to be the most difficult connection, it's pin 9. Pin 9 is the feedback pin, I believe, which is a important connection, so I can't believe I missed that. Pin 9. So just going back to this, yep, it's the feedback pin. You want to have a nice, strong connection for that. So you would want to make sure that you kind of getting straight to where you need to go with that. Let's see what they did in the reference design for that. I think they probably have a yes, they have a adjustable output regulator. So they're going through this track here, so that might be okay. We can do the same. So I'm gonna move some of these components out. Get my feedback in first. Move to the other side. Wait, another thing, if you have footprints on front and back, you can turn them off, and it makes things easier to look at. Let's move this out. I don't want to mess up my ground plane, as I don't know what's wrong with the track there. Let's fix it properly. There we go. So 3v3 there. I'm gonna put a ground wire there and take that to the other side. I think I'll just do it on this side. This design needs some work. I recommend, if you're gonna, when the video goes live, I'll upload the design files, and then, if you want to tinker around with it, yeah, it's a good learning thing. Right, okay, last thing is putting this track in place, and I don't have the space anymore for the clearance. Yeah, because I missed an important connection, it's causing me a lot of rework, so it's causing me a lot of components that I need to move around, but that's all right. That's connected, and finally you should see that we have everything connected except for these 2 points here, which can just go to the ground plane there. And what I'm going to do is make sure that, yep, they're the size of the track. I mean, that'll be fine. So the ground plane starts over here and they're connecting straight there, so that's not a problem at all. And quickly put down an edge layer on this board. Well, let me move this in here as well. That was the earlier design. Well, when I say design, that was the earlier thing that we did. Just a square box around this for now to show you that it's in a decent place, basically, and then we can tinker around with it. So you got the nice 3v3 buck converter here. All the references and everything, you want to tidy them up. Got the USB-C connector. You want to make sure that the edge of the USB-C connector and the edge of the PCB line up. So yeah, I mean, it's looking good. I mean, I wouldn't call this done. I would want to. I think there can be a lot of improvements on the buck converter, just because I did it in a bit of a rush. But yeah, it's been, hopefully the stream has been good. I'm just testing things out. So yeah, hopefully you enjoyed the video, and yeah, let me know if you want me to do more of these, because I think I did enjoy it myself as well, to be honest. I'll upload the design files onto onto the description using Gmail or something, and then you can tinker around. I mean, you can post me um, different things on how you improved it if you want, and we can review that together. That'd be good. Yeah, so thanks for tuning in, and I'll see you next time, guys. Yeah, and thanks for the interactions. Another one, Callisto. So I'm going to end the stream now. See you later, guys. Have fun.